So welcome, Professor. Professor Park is Assistant Professor of Electrical and Computer Engineering at KAUST. Prior to join KAUST, he was Associate Research Scholar at Princeton University, engaged in cross-departmental robotics project. His current research interests are in robotics, multi-robot control, feedback control theory, and game theory. So the presentation today is task allocation games, multi-robot trash collection. So Professor Park, when you're ready, the floor is yours.
All right, thank you so much for a very nice introduction, Clara. And thank you so much for Professor Eckfern for giving me an opportunity to give a speech today. And looks like today's session for the mobile robotics, we have all superstars, I guess, except myself. But the rest of the speakers, I can see that they are all superstars in their respective mobile robotics field. I'm very excited to be a part of this presentation. So again, my name is Shinkyu Park, and I'm an assistant professor. I joined KAUST about 2 months ago. So what I'm going to present today is more or less what I have done right before I joined KAUST and what I'm going to do, say, in the next few years here at KAUST. And I'm a faculty in the electrical and computer engineering program here at KAUST, and also a principal investigator in the distributed systems and autonomy group at RISC-Lab. So to give you a brief introduction to the RISC-Lab, we have currently 3 faculty, including myself and Professor Eckfern, Professor Jeff Sharma, who used to be our colleagues here at KAUST. And we are mostly doing many of the robotics research activities ranging from autonomy, distributed robotics, also aerospace, which is led by Professor Farron. And my today's presentation is going to be about the multi-robot systems research. So I titled as task allocation games and the multi-robot trash collections. So we will see 2 different components. One is more or less about the theoretical findings on the multi-robot trash collection problem. And the second part is going to be an application of our task allocation framework, a theoretical framework to address some of the challenges in the trash collection, the applications. So the motivation behind this work was when I was working at the Princeton University, we wanted to find a very nice application where a multi-robot systems research can make an impact in one of the real world challenges in our society. So what we wanted to decide to do was, what if we can make a Wall-E-like robots and make them fully autonomous? They can, coordinate with each other in order to sense and pick up trash from ground. You can imagine, trash is always our problem around the corner. And if you probably see like a pile of trash, a picture of the pile of trash in the oceanic environment. So we wanted to tackle those problems with our outcome from the multi-robot systems research. So while I was working at the Princeton University, so we started to build a multiple, what we call the mobile manipulators, which has like a mobile base, so that they can move around, also has a single robotic arm. So robotic arms are actually used to grab something from ground. And as you can see, there is a small pocket on the side of the robot. And this robot not only has a manipulator, it also has 2 important sensors. One is the camera that can detect an object from ground. It also has a laser scanner that allows each robot to detect surrounding environment. Here, the laser scanner is mainly used to detect other robots in order to do obstacle avoidance. So one of the amazing things I've learned through this implementation experiment was just allowing robots to implement a very simple algorithm on the individual robots, just to put them there in the just a confined area. They are actually they can actually move around in the space and sense the object and then pick it up successfully. As you can see, it's a bit slow, but still they are able to navigate in the space and try to sense and pick up the small object from the ground. So one of the challenges, if we think about expanding this small scale experiment to the large scale experiment, one of the challenges is going to be how we could enable the coordination between the multiple of these mobile manipulators, because I will show you why the coordination is important. But one of the most important thing we wanted to implement in this research, retrieval systems research, is to enhance the efficiency of the entire multi-level system in the trash collections. Why the coordination among the robots is important? So I'm going to show you a video that compares. So one side we have a multi-level system without coordination. On the right-hand side, we are going to show the multi-level system with a coordination algorithm implemented. So they are more or less exactly functioning in the same way, in a way that they are trying to go from their initial point, and the destination is mirrored with respect to the red dot. So you will see all the robots are trying to get to the other side of this lab space. And the scenario on the left-hand side, they are implemented with an obstacle avoidance based on what we call the artificial potential field. But on the right-hand side, the robots are implemented with the same algorithms, except that robots can communicate with each other and they decide which directions to avoid each other. For instance, if the two robots are coming together, they get to reach an agreement they are both rotating to the left-hand side of their respective directions in order to avoid each other. So what we are going to see is super amazing, because all of the robots are exactly using the same algorithm, except only the difference between the two scenarios is whether they are communicating and trying to reach the agreement to which directions they want to avoid each other. So just using the very simple algorithm, along with the simple coordination mechanism among the robots, we can actually super enhance the efficiency of our multi-robot systems. So going back to our trash collection application problem, here what we are trying to do is use the multiple robots to collect the trash, sense the collecting trash from ground. And our main goal here is to design a decision-making algorithm. And we want to make sure that this algorithm enables robots to responsive to the changing just a trash landscape. So if the landscape changes over time, we want to make sure that our algorithm actually controls or pushes robots toward the higher level of the trash landscape. So this kind of things you can think of as nice, translate into nice applications of building the Wall-E-like robots and then using them in a trash, like large scale trash collection applications. And the way we design the algorithm, we are going to use some of the principles we learned from the control feedback, control system theory. So let's imagine we have a model for how this environment or the trash landscape changes over time. And we can assume that we can measure the trash volume of this trash landscape and use it as a reinforcement signal to our multi-robot systems. And if we design our multi-agent or multi-robot decision-making algorithm using this reinforcement signal from the model we built, we could actually control the distribution of our multi-robot systems. And the distribution of the multi-robot systems would later determine which location in the trash landscape we could decrease the value of the landscape. We can reshape the shape of the trash landscape. So the way we wanted to tackle this problem is translating the multi-robot trash problem into feedback control system design problem, and try to see how we could design a mathematical model for each of the block components and try to identify what is the equilibrium state of the feedback control system and what are the conditions under which we can attain the stability. So here the stability means the trajectory of the trash volume and trajectory of the robot distribution converges to what we call the equilibrium state. So I want to emphasize that the equilibrium state in our problem formulation is very, very important, the main reason is because the system being stable, the trajectory of the robot's distribution and trajectory of the trash volume converges to equilibrium state is actually equivalent to robot being optimally distributed and the trash volume is minimized across the entire this given area. So for this reason, I'm going to first talk about how we could formulate the feedback control formulation in our multi-robot trash collection applications, where we'll be focusing on two things. Well, the first part is going to be how to model the model for this trash environment. And then the second part is going to be how we can design this decision-making algorithm that allows the entire multi-robot system to change their the distribution, the location distribution. So once we have this control feedback control framework, then the next topic would be establish the stability. And the stability, later I'm going to show you that the stability in our feedback model is associated with the performance guarantee of our multi-robot system in the trash collection applications. And then the third part is I'm going to show you some of the experimental results we have get from a physics-based simulator. So instead of using the real robot, I'm going to, for this presentation, I'm going to use the physics-based simulator in order to do some experiment with models we built from the first two topics. So before going into more details, I want to acknowledge some of my collaborators who helped me with building this nice work. I want to acknowledge Professor Yang Leonard from Princeton University and Professor Jeff Sharma, who used to be with us at KAUST, but now at the Illinois Urbana-Champaign, and my PhD advisor, Professor Nuno Martins at the University of Maryland. So our starting point is going to build a model for a trash environment. So we are going to start with partitioning our trash environment into a finite number of patches. So the size of the patch really doesn't matter as long as we end up with a finite number of patches. So you can imagine splitting these patches into finer ones. That's also fine in our framework. So once we have partitioned the environment, we are going to assign variables qi and xi to each patch. And the qi is going to be a variable that represents the trash volume in patch I, and xi represent the portion of robots working in patch I. So if you land our multi-robot systems on this gridded environment, then you could see in this specific example, we have 3 robots in the patch 1. So the value of x1 is going to be 3/14. And we have 2 robots on the patch 2. So, the value of x2 is going to be 2/14. And also in the same way, you could see that the value of x3 is going to be 1/14. So once we have this definition of partition the environment in the 2 important variables, we can actually write down the equation that describes how the waste volume in each patch I changes over time. So here our model has 2 important terms. The first term is what we call the consumption rate. That depends on the current trash volume and the portion of the robots working in the patch I. And this describes how fast this given xi number of robots can sense and pick up trash in patch I. And the second term is associated with a growth rate that describes how fast the trash grows in patch I. So for the purpose of the analysis, I'm going to assume that the Wi is a constant, but one of the important thing or the aspect of this research is we are not only considering consumption of the trash by the robots, but also the fact that the trash volume at every location can grow over time. So you can imagine that the technical challenge is robots have to make a decision to which patch to move around, considering the fact that other robots are also picking up the trash. But not only that, you have to also consider that the trash landscape actually changes over time. So once we have this dynamic model, and the next step is to design the decision-making algorithm. So what this decision-making algorithm describes is two things. The first part is, which is described by this set T, that describes when the robot can switch their patch locations. So set T will contain the set of time instances where each time instance, a robot can switch their patch location. And then another one is a mapping row, which describe how each agent, when they are given opportunity to switch their patch, how each robot will switch their patch locations. So in fact, this row is a matrix valued mapping, and its ijth element will tell us the probability that a robot that gets the opportunity to switch their patch locations goes from patch J to patch I. So looking at this definition, you can imagine that all the robots are changing their patch location according to this probabilistic law, and they use the information about the trash volume across all the patches and the robots distribution in this given area. So our main goal in the decision-making algorithm design is to select set T and the mapping row such that the waste volume across the entire area is actually minimized. So in the next few slides, I'm going to briefly discuss how we can design the set T and the mapping row. So one thing I wanted to tell you before I move forward is this is just a example we have adopted for our preliminary result. And we are still looking at how we could actually improve our selection of this parameter for the decision-making algorithm. That's a kind of ongoing working. So to start with defining set T, we use the Poisson process in order to define it. So we call it a Poisson clock. So we define set T as if T is a clock that describes when the robots can switch their patch locations, and it contains a set of time indices. And one of the technical condition here is the difference between the two consecutive time instances is distributed according to the exponential distribution with the parameter lambda. And the other way to look at this is that the time indices in the set T is actually a jump time of the associated Poisson process with the same parameter lambda. So to give you an illustration of that, is how the Poisson clock works, we are going to consider that every robot has their own Poisson clock, but this parameter for the parameter lambda for the Poisson clock are all identical. So you can imagine all the agents or the robots have a same Poisson process, independently identically distributed Poisson process. And the time ticks of the Poisson clock will determine when each robot can move their patch location. So once we have this Poisson clock for every robot, the next step is to define the mapping row JI. So again, the mapping row JI was the probability that the robot changes its location from patch J to patch I, left index to right index. And as an example, we are going to consider that the row JI is defined as the positive part of the difference between the waste volume in patch I minus waste volume in patch J. So you can see from this equation that robots switch to new patch location I if new patch location I has a higher trash volume than current patch location J. And the likelihood to change to new location will depends on the difference of the trash volume in the two patch locations I and J. And the robots tend to stay in the same patch with a 1 minus, sum over all these indices j, then this constant alpha is used to guarantee that the second equation is a well-defined probability instance. So very nice thing about this approach is actually, if you increase the number of robots to say infinity, if we have an arbitrarily large number of robots, then we could represent the change of the robot distribution as an ordinary differential equations. And that's turns this decision-making algorithm into the representation you can see in the dynamic system theory. And then this equation essentially tells the difference between inflow to patch J to outflow from patch I. By assuming that we have a sufficiently large number of robots, we could represent the change of Xi as a dynamic system, and also the change of Qi, the waste volume in patch I, also as another dynamic systems. And you can immediately see there is a feedback interconnection between these two blocks. So there is a waste volume computed by the lower block in response to the growth rate at patch I and the number of robots working in the patch I, and it produces the output Q and put it into the upper block. The upper block is determines how the robots distribution changes over time in response to the waste volume across the entire area. And one of the important thing was under our selection of the rho ij as a positive part of the difference between the waste volume in two different locations is that at the equilibrium state, when xi dot and qi dot are all zero across all the patches, this implies that the waste volume in all the locations are minimized. So you can see the importance of this feedback representation and the importance of the equilibrium state in connection with what we want to achieve in the multi-robot trash collection applications. So once we identify, write down equation for the feedback interconnection and identify the equilibrium state, next step in our algorithm design is what are the conditions under which the trajectory for the waste volume and trajectory for the robot distribution converges to the equilibrium state. In other words, what are the conditions under which robot is able to achieve the minimum achievable trash landscape and there's a trash collection applications. So as I described earlier, we are going to leverage some of the tools from the dynamic system theory. So one of the tools I'm going to use is the notion of the passivity. And the notion of the nice thing about the notion of the passivity is if we interconnect the two passive, dynamic systems, in our case, if we have a passive multi-agent decision-making model and the passive dynamic model for our trash environment, their feedback interconnection would result in stability. Here, the stability would imply that trajectory for the waste volume and the trajectory for the robot distribution would converge to our desired equilibrium state. So this notion of the passivity actually came from circuit network theory. So in the circuit network theory, the passivity implies the following. So passivity of the circuit network implies that the change in the stored energy in our circuit network is no larger than energy supplied to our circuit network. So you can imagine if the circuit network is mostly composed of resistors, which is energy consuming components, then you can see if you apply voltage, if you connect the power source to your resistive circuit network, your circuit networks tend to consume more energy. So energy actually stored in the circuit network would be smaller than the actual supplied energy from the power source. And then on the other hand, the circuit network that is not passive is an amplifier. So you can imagine if you have experience with playing a musical instrument and had a chance to use the amplifier, you apply a small acoustic signal to the amplifier, and the amplifier's role is to actually increase the acoustic signal and then speak up through the speaker of the amplifier. And if you are imagining connecting this non-passive amplifier systems with, say, another instrument, guitar, and then if we put the strike the guitar string and then put it in front of the amplifier, what happens is that acoustic signal is going through between the guitar pickup and the amplifier, and then the acoustic signal never dissipates over time. So this kind of behavior you will see in the non-passive systems, whereas in the passive systems, they tend to consume and dissipate this energy over time. So same analogy could be applied in our trash collection applications. If our two models in the feedback, our feedback framework are both passive, what would likely happen is defining the energy in our application as trash volume, then the trash volume would dissipate over time by the passivity of the two components in our feedback model. So going back to our multi-robot decision-making research, we are going to apply the same notion of the passivity to our two blocks. So for the in the first case, the passivity for the dynamic model that describes how the trash landscape changes over time. Here, similar to the circuit network, you could define the notion of passivity as the stored energy in our dynamic model of the environment is no larger than energy supplied to our lower block. So this is more or less a technical conditions our dynamic model has to satisfy in order to be a passive dynamical systems. But the important question is really, when is a dynamic model passive? So interesting thing here is actually the passivity, notion of the passivity for the dynamic model is related to the manipulation capability and perception capability of our multi-robot system. So to see these, so one of the we have two technical conditions, and one of them is when the number of robots increases, then in order for the dynamic model to be passive, the consumption rate has to increase as well. So you can relate this technical condition as a robot's manipulation capability, that as we increase the number of robots working in the same patch, their capability to pick up trash increases as well. And the second technical condition is when the waste volume increases, that also contributes to improving their consumption rate. So what it means is that as the volume of trash increases in the patch I, this technical condition would guarantee it if the robots have a perception capability for them to easier to sense the trash from ground. If they see they have more trash in the same patch I, and that will result in increasing the efficiency of their trash collection capability. So the passivity for our dynamic model is more or less associated with the robots, this robotic team's capability in the manipulation and the perception. And the second part we have to discuss is the passivity for decision-making model. So here, similar to the previous slide, the passivity for the decision-making model is defined as the stored energy in the upper block is no larger than the energy supplied to the second block. And luckily, under our selection of the rho JI, which appears in the upper block as a is a positive part of the difference between the trash volume into different patch locations. Under this selection of rho JI, we could actually explicitly find this function as that satisfies this inequality. So once we have the passivity established for both blocks in our feedback diagram, what we can see is two inequalities. If you sum them up, the left-hand side would become the stored energy in the entire feedback control system. And the right-hand side, they actually cancel each other. So if you sum them up, the resulting inequality tells us that stored energy in this feedback loop never increases. It will either stays in the same energy state as initial one, or it will decrease. What a little bit of the more technical tricks you can use, you can actually show that the stored energy in the feedback loop goes to 0, which is the lowest energy level. And this energy level converges to 0 actually implies the robot is capable in the long term. Robot is capable to minimize the trash volume across the entire patch locations. And many of the tools I use here is coming from one of the earlier work I did with the Professor Martins and Professor Shama. And there is a nice tutorial paper we presented in the CDC in 2019. If you want to learn more of the details of the technical details, I would highly encourage you to look at this paper. So now we have the working model and feedback system that guarantees the multi-robot systems to effectively pick up trash and then minimizes the trash volume. But everything was a built-in theoretical framework. Now let's look at what this theoretical framework translates into in the trash collection experiment. So in this trash collection experiment, we are going to have 4 rectangular patches, and robots are tasked with moving into one of the patches and collect this red rectangular object. So we are pretending this red rectangular object is a trash on the ground, and this red rectangular object actually is keep introduced in all of the patches according to a Poisson distribution with it's a parameter rate WI. That this WI was coming from the growth rate of our dynamic model for the environment. So as I explained earlier, the growth rate, I assume that it's a constant, but in the experiment, we are actually introducing the new ways to at a random time according to Poisson distribution. So in the experiment, you will see our model is not 100% accurate, but it will be just approximate of it will just approximate how the waste will change in the every patch. And then robots, as you can see on the left figure, it has a mobile base with a manipulator. So if it sees a red object in front, it will try to reach with the manipulator and pick it up, and then put it into. It has a small pocket in the behind. So one of the assumptions we are going to make is a small pocket can only hold up to 10 red objects. So if it reaches its maximum capacity, this mobile robot will visit one of the closest dumpster area and then pretend it will just empty their objects in the pocket in one of the dumpster areas. And for the decision-making model, we are going to adopt the one I have described before, where the parameter for alpha is where the alpha was written down. I've selected alpha as 1/600. So this is only to guarantee that this entity for every index j is a well-defined probability entity. And I select the parameter for the Poisson clock, lambda equals 8, which means that the robots are allowed to change their patch location every 8 seconds on average. And all the experiment I'm going to show, the robots are going to have equally distributed to begin with. And if you are interested in seeing the more details of the implementation, there is a ICRA paper. It's not available yet, but it will be available hopefully after this ICRA conference. So I would encourage you to take a look at this conference paper. So I'll start with a video that shows how these robots are actually working in the simulation environment. So to begin with, they do have a implementation of a simple collision avoidance and individual surveying in order to place yourself in front of this cubical object and then pick it up and put it into their pocket. And according to their pause and clock, they are allowed to switch their patch locations, and when the pockets are full, they have to visit the dumpster area to empty them. But here I'm not illustrating anything for the dumpster area, but it's we are just pretending as long as the robot is visiting the dumpster area, they can just empty all the cubical objects from their pocket. So in the next few slides, I'm going to show a few of the experimental results we have. In the first experiment, we are going to see how our decision-making algorithm is responsive to the changes in the environment. So we start with having the most waste in the fourth patch and the least waste in patch 1. So mobile robots will start to move toward the patch 4 in the beginning, but growth rate I select as a 1 to have the highest growth rate. So what I wanted to see in this experiment is initially they all moved to, or majority of the mobile robots moved to patch 4 because patch 4 has the most trash to begin with. But because the growth rate in the patch 1 is highest, they tend to slowly move to patch I, and eventually they actually converge to the large portion of the robotic team converges to patch I, and the last are remaining in patch 4. So as I mentioned, patch 4 has the most initial waste volume. The robots are moving from their initial locations all the way to the patch 4. But because patch 1 has the highest growth rate, as time goes by, as the trash volume increases in the patch 1, robots tend to move from patch 4 to patch 1. And once they are done with collecting trash from patch 1, they'll move to other locations. And then one of the interesting thing you can see is based on a proportional to the growth rate, robots are more or less with some oscillation, they converge to the robot distribution that is proportional to the growth rate in the 4 patches. So in the second experiment, what we are going to see is that there are going to be a surge of trash in the first patch. So at time t equals 500, we're going to see a high peak in the trash volume in patch 1, and you're going to observe how our robots going to respond to high pitch in the trash volume in the patch 1. So we start with the initial condition where the trash volume in every patch is equals to 0, but because of the non-zero growth rate, the new trash is to keep introduced into the 4 patches. And when it comes to time t equals to 500, we are going to consider that the trash volume in the first patch suddenly increases, and then you can see that all the robots are moving to patch 1, and then once they're done with removing trash from patch 1, they go back to their the initial locations. So one of the observation you can make once this animation goes all the way to the end is we start with approximately uniform distribution of the robot distribution, and when there is a surge in the trash volume in one of the patches, everyone moves to there and then comes back and then try to maintain the same uniform distribution as in the first place. Right. And the third case is the case where there is a switch in the growth rate. So we start with all identical 0.5 growth rate for every patches, but at time t equals to 500, one of the patch 1, its growth rate will change to 1.5. So what I want to see here is we start with the equal distribution of the robots according to the equal growth rate all the patches, and whether the robot has a capability to redistribute their patch locations in order to accommodate this switching in the growth rate. So as in the previous example, we assume that the growth at the trash volume in every patch equals to 0, but you still have a growth rate, non-positive and non-zero growth rate. So robots should work in the patch to remove the trash, and initially they have a uniform distribution because the growth rate across the entire patch areas is all identical. But at time equals to 500, the growth rate at patch 1 actually increases from 0.5 to 1.5. So you can see the robots are redistributing their locations, and they're putting more individuals, robots, into first patch. And they maintain a certain level, approximately the same level of robot distribution in all other patches, the patch 3, patch 2 to patch 4. So you can see the robot, under our decision-making algorithm, robots is able to actually sense the change of the growth rate and redistribute their distribution according to the change, the growth rate in our trash environment. And the last case is the case where we start with the 40 robots, and at time equals to 500, we assume that the 15 of them are not working. So we will have only 25 robots in between time 500 to time 1500, and then the malfunctioning 15 robots will come back to life at beyond time equals to 1500. So same as before, we have 0 initial condition for the trash volume, and the growth rate are all identical across all the patch. And here the red black line describes the portion of the robots that is not working. So initially we don't have any failed robots, but at time equals to 500, there are 15 robots that stop working. So here the yellowish dot represents a robot that is not actually working. So interesting thing here is even if some of the robots, like randomly selected robots, are not working, the rest of the robots are able to distribute themselves in this trash collection applications. So because the growth rate is all identical in the all 4 patches, the ideal distribution of the robots has to be approximately uniform. So as you can see, between the time 500 to 1500, they are, with some oscillations, they are approximately maintaining this equal uniform distribution across all the patches. And once the robots are back in life, the failed robots are back in life, you can see they are going back to the normal operation where as if there was no a failure in the system. So you can see our decision-making algorithm in this example, actually guarantees the resilience, in some form of resilience in the failure of the individual robots in the system. So what I have shown you through the experimental results is using very simple decision-making algorithm, which merely depends on just looking at the instantaneous value of the waste volume across all the patches. Robots are actually able to cooperate with each other and successfully reduce the trash volume to the lowest achievable value. So one thing we wanted to investigate is whether we could improve our decision-making model by incorporating the parameter from our dynamic model. So one of the nice thing about our simple algorithm is this algorithm guarantees a convergence to the equilibrium state without knowing anything about the parameter of the dynamic model. So robots are only, as long as robot is able to assess the current trash volume in all the patch locations, they are able to effectively remove trash. But we wanted to see if we incorporate some of the knowledge from our model, can we improve the performance of our multi-robot system in the trash collection? That was a kind of research question we are currently looking at. So to give you a preview of what we have found so far is assuming that the robots know this parameter of the models, Fi, the consumption rate, and then Wi, which is growth rate. And then we incorporate these two parameters into our decision-making model. So here we are going to switch the variable for the algorithm from Qi to Pi. And here Pi is going to be a combination of the waste volume in patch I plus a scaled version of this term. So second term can be interpreted as how much capability the robot team is putting in comparison with the capability, the consumption rate they have to maintain at the equilibrium state. So you can see, depending on this value of nu, if nu is 0, it goes back to our simple algorithm. If nu becomes larger and larger, then we are simply assigning or selecting the robot distribution at the equilibrium state. So it's more can be interpreted as whether you make the system by decreasing nu, whether we make a system more responsive to the instantaneous value of the trash volume, or we want to pre-relocate a robot in such a way that the robot's distribution becomes very similar to the robot distribution at the equilibrium state. So the selection of this new value is very, very important. I will show you one of the early experimental results. So left-hand side, we are seeing the same as before. The robot is selecting their patch locations only with the trash volume information. But on the right side, robots are selecting patch location according to the new model. And then this new parameter in the new model, I set it as a 40. So I would say this is I figure out that 40 is a kind of a well-working selection through the trial and error. But if you see the result at the nu equals to 40, robots tend to move around the different cells, but as time goes by, they stopped changing their cell locations less frequently than the previous case. And as you can see, the oscillation in the trajectory of the trash volume becomes less significant compared to the previous one. So our conclusion here was, with a proper selection of the parameter in the new model, we can actually reduce the oscillations in the trajectory. That's one thing, and we can also see there is a small improvement in the convergence rate as well. But the selection of the nu is very important, because if you select the too high value for nu, what would likely see is robot is no longer responsive to the instantaneous value of the trash, and they prefer to pre-locate themselves in an equilibrium state. So we don't see much change in the robot's patch locations, and it has a worst convergence rate on the trajectory of the trash volume. So looking at these two experimental comparisons, you can see that nu is actually a dial you can use to make systems responsive to the changes in the environment, or it could make the switches of the patch locations less frequent. That may result in conservation of their energy consumption, but it will result in significant deterioration in the convergence rate. So I want to conclude my presentation with a summary that in this work, I have described how we could build a feedback interconnection model in order to tackle a multi-level coordination problem. And also I showed how we could design algorithms for decision-making in the multi-level coordination such a way that the stability of our feedback model is guaranteed, and also show that how this feedback system approach for the multi-level coordination can be translated into the algorithm and the experiment in the trash collection application. So our target application, we started with a trash collection But yesterday I saw a very interesting presentation from a graduate student in the Red Sea Research Center that we can also use the drones to map coral reef and the Red Sea. I think if we are allowed to fly multiple drones there, I think this type of multi-level coordination research also can be applied in the different applications. All right, with this, I will complete my presentation. Thank you so much.
Thank you very much, Professor Park, for your very interesting presentation.